Alright, so smoothly isomorphic matrix groups have isomorphic Lie algebras. Alright, now that's a corollary, I would assume, to the theorem we just got done looking at. So if I have F goes from Lie group G1 to Lie group G2, matrix Lie groups of course here, if that's a bijection and a group homomorphism, that means that dFi is a Lie algebra homomorphism, right? But F is 1 to 1 at I, that means that dF is also 1 to 1 at I, and so that means that its kernel is trivial. In other words, dFi is an isomorphism, right? So it's a linear isomorphism which preserves the bracket. Therefore, G1 is isomorphic to G2 as Lie algebras. There you have it. So examples of this abound. So let's see here. SO3 looks like this. SU2 you could write as such. They're both three-dimensional, right? And also SP1, three-dimensional. Now he places some brackets around IJK, I think, to emphasize that they're these are the versors. Anyway, so if the elements above are denoted A1, A2, and A3, in each case, A1, A2, A3, A1, A2, A3, A1, A2, A3, the same pattern holds for all three of them. The bracket of A1 and A2 is A3, the bracket of A2 and A3 is A1, the bracket of A3 and A1 is A2. So they all have the same bracket structure. So any mapping which sends A1, quote unquote, to its corresponding A1 will uniquely, linearly extend to an isomorphism. In particular, the Lie algebra isomorphism between little SO3, little SU2, and little SP1 is as follows. This goes to that, it goes to that, these are interchangeable, etc. for the others that I've now gone up. So these Lie algebras are isomorphic, but that's not to say, of course, that the corresponding Lie groups are isomorphic. That requires global topological data, which the Lie algebra does not reveal to you. So here's a comment. The special unitary group of order 2 is smoothly isomorphic to SP1, the symplectic group of order 1. However, SO3 is not isomorphic to SP1 because it turns out the global topology of the group is not revealed by the Lie algebra. So two non-diffeomorphic groups may have the same Lie algebra. So if you have two Lie groups, and they have the same Lie algebra, it doesn't tell you that they're the same Lie group. However, if you have two Lie groups and they have different Lie algebras, that does tell you that they're not the same group. So it's kind of a no-go theorem, but it's not a, it's useful, but it's not a deal breaker for them. It may or may not be that they're isomorphic if their Lie algebras match up. All right. More to say about that as we go on here, but so that brings us to the topic of the adjoint action. So we have a matrix Lie group, dimension D, that has a tangent space which is d-dimensional, right? So it's isomorphic to RD. So with the choice of basis, well, of course, with respect to some choice of basis for G1, the adjoint from G to G is a linear transformation, and so you can look at the adjoint in terms of a D by D matrix A, and that is the so-called adjoint representation. So adjoint of G is LA for some A and D by D matrices. However, better yet, since the adjoint of G is invertible, all right, since the adjoint of G is invertible, it is an isomorphism, and that means that A in the D by D matrices, therefore A is actually an invertible D by D matrix. So in total, the correspondence G goes to the matrix of the adjoint, gives you a function from G to the D by D invertible matrices, GLDR. Okay, so when you have a function that goes from a group to a set of linear transformations, that's called a representation, all right? Although I think the notion of representation is more general than that. Anyway, sufficient to say that representation theory is a subject which is alive, well, and being ever more generalized with each passing generation, more deeply understood with each passing generation of mathematicians. Anyway, so lemma 8.8, the adjoint goes from G to GLDR is a smooth homomorphism, and that's with respect to any choice of basis. All right, let's say beta for convenience of exposition. The proof is as follows. So the adjoint of G1, G2 of X is, by the way, these arguments are pretty simple because everything is matrix multiplication. It would be fun when you go on to kind of come back to this and look at how much simpler it is here as opposed to if you do this in the abstractly group. There's a lot more, as I recall anyway, it seems like there's a lot more baggage because you have to fight through other identifications and such. But oh, anyway, let me shut up about that. So here we go. The adjoint of G1, G2 is G1, G2, X, G1, G2 inverse, but sock shoes gives me that that's G2 inverse, G1 inverse. But of course, if you just look at the inside story here, that's the adjoint G2 of X, and then that's the adjoint G1 of that guy, right? So therefore, adjoint G1, G2 is adjoint G1 composed of the adjoint G2. Well, that's good. That means that there's a homomorphism of group multiplication to composition of linear transformations, and then correspondingly, the matrix of those linear transformations likewise preserves this homomorphism property by basic linear algebra. Of course, the matrix of a linear transformation is, and matrix multiplication itself is so defined as to enforce this homomorphism. Anyway, smooth, well, there's a formula, so it's smooth. All right. Only slightly kidding. All right, the adjoint action of G on G. So I'm going to stop here and pick it up again.